This video is about differentiating inverse trig functions, and particularly questions where there's a little bit more to it than just the standard inverse trig. Maybe you've got a little bit of product rule and so on. So let's have a look at an example. So this question requires me to find dy dx given y equals x squared sine inverse x. Well, note first of all that in this question I've got multiplication going on, and in both parts of the multiplication I've got an x variable. So that means that I am looking at product rule, and I'm going to call the x squared u, and the sine inverse x is going to get called v. And of course then I'm going to want to differentiate both of these. Well, it's easy to get the du dx, that's just simply a question of differentiating x squared, and that'll just give me 2x. But the v equals sine inverse x will take a little bit more work. And just like in previous questions, I'm going to start by bringing that sine inverse over to the left. Now I'm not differentiating yet, I'm just setting myself up in such a way that I can differentiate this particular equation. And to follow on from rewriting it as sine v equals x, I'm going to want now next to draw my triangle. So I'll first of all note that x can be written as x over 1, that'll just make it a little bit easier for me. And then I'll draw my right-angled triangle. I'll fill v in as the angle. And then, knowing that sine is opposite over hypotenuse, I'll fill in x for the opposite and 1 for the hypotenuse. And then I want to find that missing side of the triangle, which I will find using Pythagoras. In this case, that comes out as the root of 1 minus x squared. I'm now going to differentiate using implicit differentiation the statement sine v equals x. So that's going to give me cos v. I mustn't forget, of course, to differentiate my angle. My angle v when differentiated here will give me dv dx. And the x on the far side of the equal sign will differentiate to give me 1. Now I want to get dv dx by itself. So I'll just bring the cos x across, the cos v I should say, across and divide it into the 1. And glancing back to my triangle from previously, I'm going to be able to make the cos of v using the adjacent and the hypotenuse. So in this case, the cos of v is the root of 1 minus x squared over 1, which can be written as just root 1 minus x squared. Okay, so now I'm going to return to my product rule. And I'm going to just continue filling in these portions that I'm going to use in the rule in a moment. So I've got my u, du dx, my v, and now my dv dx, which we said was 1 over cos v, is going to be 1 over root 1 minus x squared. It's a pretty good idea to write down the rule that you're going to use. In this case, that's the product rule, so I've made a note of it here on the page. And now it's simply a question of just slotting all those pieces of information that I've written down up here into that formula. So in this case, dy dx equals to u times dv dx plus v times du dx. And it's absolutely fine to have a sine inverse x in my answer. In fact, I kind of expect it if I ever run into product rule or quotient rule or chain rule in an inverse trig differentiation. And I'm going to tidy up a little bit more just to finish off by putting the x squared over the root 1 minus x squared and sticking the 2x in front of the sine inverse x. And there's my solution. If I happened to encounter a quotient rule question, I'd take the exact same approach as I have here by writing down my u, v, and then my du dx and dv dx, whichever one was easiest to work out, and then simply going through the process of dealing with the inverse trig differentiation, filling it in for whichever of these it was, and then substituting into the correct formula.